Uh, as you know, these are the tutorial lectures going on, and we are on our 4th tutorial lecture, and the total number of the lectures is 42nd lecture. Today we will have 42nd and 43rd lecture also. I'll split it. You can watch whenever you feel like. So yesterday we uh, uh, covered chapters up to chapter number 5, that is the lightning and lightning or protection. We talked about the lightning protection, and yeah, this was the last figure I gave you, how to protect the transmission line with a grounded conductor on the top. Two philosophies, an angle, cone angle of 30 degrees and 45 degrees. The 30 degrees is stringent when you want to be more or less sure that lightning will not struck upon the live conductor. That is what one should. But as I told you, it does. Lightning is so unpredictable. It does sometimes strike upon, in spite of the protection provided, it does strike upon the live conductors, and that is how the lightning over voltages in the form of traveling waves produced. So we will go to the next lecture. I'm sorry, next problem that is on chapter number 6, where we have dealt solid and liquid dielectrics. As I mentioned several times, it would be very much advisable to refer to our book, because I am following everything from our book. So this, please read this example, and we will, and you make your own break with this example. After an attempt, bring your pen and paper and attempt this numerical number 8. Uh, just a minute. Yeah. You are being asked in this question, calculate the electric power loss, that is in real power loss when we talk about the watt per kilometer and charging current in ampere per kilometer of a 110 kV XLPE insulated cross-linked polyethylene insulated single core coaxial cable having the following dimensions. In fact, we have, if I'm not mistaken, the question number 2 is very similar to this one. This one is slightly simpler because it is not given here that the semiconductive sheaths are provided over the conductor and below the outer conductor, or on both sides of the insulation semiconductive sheets are provided, but in this example it is not given, so it makes it slightly simpler. And the copper wire stranded conductor diameter is 20 millimeter, the diameter, mind it, and the XLPE insulation thickness, that will be RO minus RI, or D, is 18 millimeter, and outer lead sheath, once again this cable is provided lead sheath. Lead sheath is provided to protect the cable insulation from any moisture ingress, because these cables are laid underground and there will always be moisture, so the insulation must be protected from moisture, and for that lead sheath is provided, although lead is very heavy metal and is not, I mean, it's not desirable, but it has to be provided. The dielectric loss factor X of XLPE is given, tan delta is given to be equal to 2 into 10 to the power of minus 4, and the relative permittivity of that is epsilon r of XLP is 2.3. So you attempt and stop the video and then put it on again to see the solution. Okay. Yeah, as you can see, in what we consider the voltage, the 110 kV is the rated line to line RMS value of the cable, and for each single core cable are used for each phase. So the potential difference across the dielectric of the cable is between the high voltage point and the ground. And ground in all these connections, you can say the start point is ground, or otherwise the between the high voltage point and the ground, the phase, the voltage will be which voltage? Line to line or line to phase? It will be line to phase. Sorry, line to line or line to ground? It will be line to ground. So line to ground, that is the phase voltage, actually will be 110 kV divided by root 3. Oh, there's a slight mistake here. It has been given here, not, it should be 110. This should be 1 here. This is 110. That is the rated voltage. 100 is not the rated voltage in our country. So 110 kV is the, it should have been there. I hope you can verify if the voltage, again, there is a mistake. It has been taken to be 110. So you correct in, oh, it has been taken correctly here. So you verify with your calculator whether it has been done with for 110 or 100. The results, you must verify. So you determine the capacitance that you have known. We have discussed in the class also in the lectures. The capacitance formed by the coaxial cylindrical cable is 2 pi epsilon naught epsilon r upon ln Ro by Ri, Ro by Ri, and is work out Ro by Ri same dimension, so it will work out. Epsilon r has no dimension, so the dimension of epsilon naught, that is farads per meter, will be, and epsilon naught is 8.854 into 10 to the power of minus 12 farads per meter. Epsilon r is given to you 2.3, and Ri is the half of the 20 millimeter, the diameter of the conductor, plus 18 millimeter thickness of the dielectric, makes Ro to be 28 millimeter. If you put everything, it should work out to be like this. You verify, okay? And then the charging current of any capacitor, because the dielectric forms a capacitor, and this will be omega Cu, and U, this is, you can say U naught. This is also U naught, mind it. Find out the U naught. So when you put these values, 2 pi C, what you have calculated in farads per meter, and the voltage has been converted into volts. So the current works out to be in ampere per kilometer. You are requested to verify whether it has been done for 100 by root 3 or 110 by root 3. It should be for 110 by root 3. Please verify, okay? And AC power loss due to AC voltage applied is given once again. You have learned in the chapter of solid and liquid dielectrics. That's valid for mm, for all dielectrics. Omega c u square tan delta. If you work out, this is in watt. This will work out in watt. Omega naught u naught you have to take, and or you can take PAC is equal to IC, the charging current, multiplied by u naught tan delta. The same thing. So when you put these values, the power loss, AC power loss per kilometer in the cable will be 31.5 watt per kilometer. If you see at 110 kV, the actual power loss, the real power loss, is to the tune of 31.5 watt per kilometer. It's not too much. Why is it low? Which parameter here determines the whole scenario? It is the capacitance formed. And as you know, in the capacitance, of course, the dimensions of the cable, and otherwise the epsilon r, the relative permittivity of the dielectric what you are using. If you had used some other dielectric and the epsilon r was higher, for example, for paper, impregnated paper cables, it is more than 4 epsilon r. So the losses would have been very high. So epsilon r determines the losses, and it is desirable to have a dielectric with lower relative permittivity to check the losses. So that is the reason that XLPE or polyethylene as such, polyethylene is not is always cross-linked and used in high voltage cables, and polyethylene XLPE rather has taken over as the most suitable dielectric for high voltage power cables all over the world, and I have seen it getting more and more use over the last 50 years. 50 years back, the scenario was completely different, but today XLPE has taken over until another very good dielectric comes up. A lot of research is going on to develop newer dielectrics with the nanoparticles, with the nano material combined with plastic material, and a lot of research is going on. You don't know, one day a better dielectric comes up. Okay, so we go to the next problem. Problem number 9. This problem is about the next chapter in the book, and that is the generation of high test voltages. So this problem actually is given for a high voltage DC generator. You know one thing, the half-wave rectifier circuits are put in cascade for the generation of high voltage DC, and voltage doubler circuit is used in that popularly, which was given way back. The voltage doubler circuit by Cockcroft and Walton was given in early 20th century, for the generation of high voltage DC. So that is still being continued. And as you would remember the diagram, you should turn over your notes to see the diagram. C1 is the capacitor, as you can read here. C1 and C2 are given capacitor. C1, you always charge the generator, or each stage is charged with the help of a capacitor, and that is C1. And otherwise, we have we have given in the multi-stage generator C1 prime, isn't it? So and C2 is the smoothing capacitor. The values of the charging and the smoothing capacitors are given 0.1 and 0.5 microfarads. And C2 we have denoted in multi-stage generator as C1 prime. So C1 and C1 prime we have given the designation. If you have your notes, you can open the notes and you will know that. And the supply transformer secondary voltage output is 125 kV. Of course, this is the RMS value of the transformer secondary voltage at a frequency of 50 Hertz. And if the load current to be supplied a magnitude of current of the order of 5 milliamperes. I mean, the load current when you test a capacitor, you always test a capacitor with high voltage. So the load current for a capacitor on applying DC high voltage is very, very small, and it is being given here 5 milliamperes of current. And find the percentage ripple. We have also learned that in spite of the smoothing capacitor there, they will over the cycle, AC power frequency cycle, there will be a dip in the output voltage, and so you have to find out the percentage ripple in the output voltage, DC output voltage, and the voltage drop, magnitude of voltage drop, and also the voltage regulation you have to choose about. Okay, so as you now attempt and stop your video, attempt with the help of your notes and whatever you learned so far, I'll then give you the solution which you can take time to open. Yeah. So ripple is given in the form of delta U. That means the you can say the change in the voltage. That is the peak value of the voltage, because the peak value ideally you should have continuously peak value if there is no ripple, no potential drop across the smoothing capacitor, the DC voltage I'm talking about, the output is DC voltage. So for single stage, we have known then that delta U is given by I1 T is the time domain, what you are considering. That means 1 upon T is the frequency, upon C2 in our case is instead of, so we have in the book defined C2 to be equal to C1 prime. C2 for multi-stage, we have taken C2 is to be equal to C1 prime. Okay, and so the percentage ripple will be given by delta U, that is the drop in the voltage, multiplied by 100 upon 2 pi V may that is omega 2 pi 1 upon F is taken care of. So 1 upon T is F. So you have sorry 2n V max. Here n is the magnitude. No, n is the number of stages. N is the number of stages. And it is given in your example the two circuits in series. It is given two circuits in series. That means the generator has two stages. So delta delta U 100 upon 2n V max, or U max you can say also, whatever we have taken normally instead of V we have taken U max, and U max will be uh, I mean, it is being taken here in RMS value. Delta U is also calculated in RMS value. So when you maximum voltage is 125 kV RMS, when it is being taken, when you are taking delta U also RMS, then to max also being taken to be in RMS, both sides. Okay, so that works out to be 4%. The percentage ripple works out to be 4%, and which n is equal to 2 here. Okay, if you are taking, got it, both sides, so the percentage ripple works out to be correctly when you are considering the both the voltages of RMS value, because there is U on the numerator and U in the denominator also. Okay, then the voltage drop is given by I1 upon F, 1 upon C, yeah, 1 upon C1, and in upon 2, 1 upon C, 1 upon 2 C2. You mind it, that each stage, this is two-stage generator, each stage will have identical capacitances, C1 as well as C2, or C2 as we have learned is C1 prime and C1 prime, and C1 in each stage will be equal to C1, you can say. So that together the voltage drop across the capacitor would work out to be I1 is given to you 5 milliamperes, 5 into 10 to the power of -3. F is 50 hertz, and the C1 capacitor is given to be, the charging capacitor is given as 0.1 microfarad, and the smoothing capacitor 0.5 microfarad. So the voltage drop works out to be 11 kV. And the voltage regulation will be given equal to voltage drop into 100 upon 2n V max or U max. So that works out to be 2.2% the voltage regulation. You know what is regulation? That means when you have the magnitude of the voltage when there is no load, and the magnitude of the voltage when there is full load. So what is the percentage of voltage drop because of applying the full load? And that is the voltage regulation. So that is that will work out this way: voltage drop into 100 upon 2n V max. So because you have calculated for the full load the voltage drop, so when there is no voltage drop, that means you are having the peak value of the P or the maximum voltage at the output. That means that will be achieved only when there is no load. So 2n Vmax or 2n Umax it will be. Okay, so this is how the voltage regulation of the test generator, high voltage DC test generator, determined. So you have the solution. You should be able to get the uh, values. So we go to the next question. Yeah, this question is again on the high voltage DC test generator, and you can say again Cockcroft and Walton voltage multiplier uh, voltage multiplier circuit. It should have been there with smoothing capacitor. A voltage multiplier, you can write here, circuit. Voltage multiplier circuit with, this is being talked here, smoothing capacitor. With the smoothing capacitor. All equal to the smoothing capacitors are normally in multi-state, they are all equal of the order of 0.5 microfarad. The supply transformer secondary output voltage is 100 kV, unlike in the previous example 125 kV, at a frequency of 50 Hertz. If the load current to be supplied is 5 milliampere, once again, the percentage ripple, again, voltage drop and voltage regulation, you have to calculate. So it is more or less a similar problem as we have dealt in the previous case. So let's not, you should be able to do it. You know that the delta U, what is delta U? And yeah, the main thing here is a the if the current is 5 milliampere and the percentage ripple voltage ripple, there is one Cockcroft-Walton voltage circuit has 6 stages. Yeah, this is what we mind it. This is a multi-stage. That the previous example you had only 2 stages. So this is a very high voltage generator having 6 stages. That means the number n here is equal to 6. So the slight different calculation will be there. Delta U will be given by I upon 2FC and the number of stages in series that work out to be n into n plus 1 upon 2. So you take care about that and attempt. So now you can open your video once again, and as you can see here, this delta U equation is slightly different for a multi-stage generator, and this is here n into n plus 1 upon 2. So this here n is equal to 6 has been taken into consideration. So the you can say the ripple voltage is of the order of 21 kV. 6 stages 100, so it would be the total rating voltage of the no load rating voltage of the order of 1200. Yeah, 1200 kV voltage doubler. You know, voltage is doubled in 6 stages. So 200 double 1200 kV. This is a very large DC voltage generator. So the ripple is 21 kV, the drop in voltage, you can say, and the percentage of ripple then works out to be 1.7%. This way, delta U into 100 upon 2n V max, and V max is taken to be 100 kV. So this everything is in RMS value, 1.75 percentage of ripple, and voltage drop can be calculated for six stages. You know, is I upon CF, and when 6 stages, it will be 2 by 3 and 3 plus n square by 2 minus n by 6. So the voltage drop works out to be of the order of 322 kV. Imagine how 322 kV because of very high current being drawn, that is 5 milliamperes. I is 5 milliamperes of current. So it's a very large current actually for DC generator. So 322 kV will be the voltage drop, and the voltage regulation is you check this value. Please check this value if 320 is correct. Please check. I can't do that here right now because of the time limitations. Please do check. It appears to me a little high. And the voltage regulation is given, as I said, when there is no current flowing and when there is full current flowing, the drop in voltage difference, and that works out to be voltage drop as calculated for the full current. That is 5 milliamperes, isn't it? 5 milliamperes of current is given here. This 5 into 10 to the power of minus 3, 5 milliamperes of current. How much the voltage drop you have calculated, and when there is no current being drawn, that means there is no load, what will be the output voltage? Or you can say the load is no load, or the load is infinity. You can is one and the same thing. There is infinite resistance load is being connected. That is, no current will be able to flow. So that works out to be the regulation of the order of 21.46%. Okay, so here we make a or we can perhaps, or we'll come to the measurement in the 43rd. Okay, so let's make a break here, and you attempt this and then open for the next lecture. That will be a separate lecture video. That will be the lecture 43, the next one. Okay, then see you there.